Welcome everybody to this webinar. Thank you for joining. So the topic today is accelerate your machine learning application on the CMC FPGA GPU cluster. And the main objective is to present a new infrastructure. It's a FPGA GPU cluster that CMC has recently deployed at University of Waterloo, and today it is available to access by Canadian researchers. And the best way to introduce this cluster is to show you a use case for it, which is a machine learning application. My name is Yassin Hariri. I am senior engineer at CMC Microsystem. And my full focus at CMC is to support research in the area of heterogeneous computing and acceleration of machine learning frameworks in the edge and cloud. So let's start with the agenda. So after a quick introduction of CMC Microsystem, we are going to present the CMC Cloud FPGA GPU cluster. Both hardware and software architecture will be presented. Then summarize one of the important platforms we are supporting today is the end-to-end deep learning platform, which is a platform that supports research in AI and machine learning from an embedded edge computing unit to a cloud-based, more powerful heterogeneous processing cluster, which is the one we are going to talk about today. Since the use case is machine learning, so we selected Caffe as a framework for the demonstration today. And before going to the demo, we need to give you a high-level overview for people who are not familiar with Caffe. And this will allow you to train any convolutional neural network model on any data set using the cluster. And this background consists of the 4-step. The first one is data preparation, CNN model definition, solver definition, and model training. So we are going to go through these steps very quickly before the demo, so you will understand the demo. The demo consists of 2 parts. The first one is to demonstrate the acceleration of Caffe on one of the most powerful GPU in the world today is the Tesla V100 GPU, and they demonstrate the inference on the Alveo FPGA card, which is a card from Xilinx, very powerful card as well for inference. And we're going to show the whole software stack for this cluster, and we're going to conclude with the Q&A session. CMC Microsystem is a not-for-profit corporation, federally incorporated since 1984. The main mission is to manage the Canada National Design Network and deliver micro and nano innovation capabilities across Canada. The National Design Network is a Canada-wide collaborative project between 66 universities and colleges and growing to connect 10,000 academic participants with over 950 companies. And the main goal is to design, make, and test micro and nano system prototypes. We measure annually our outcome by the number of publications, awards, patent awarded, industrial projects, new startups, and trained HQP moved to industry in Canada. CMC basically deliver key services to increase researchers and companies' innovation capabilities in Canada. This include design tools, CAD tool software, fabrication services to create working prototypes, equipment and services for prototype testing, platform technologies, training support networking, and technology plan and road mapping. The products and services can be grouped in 3 broad categories: CAD, Fab, and Lab. CAD consists of services for making working prototypes, which is use a selection of high-performance CAD tools and design environments, which can be available through your desktop or through the CMC Cloud. And each CAD tool and methodology, we offer user guides, application notes, training material, and courses to enhance our researchers' experience using this infrastructure. As for Fab, it consists of services for making working prototype, which include multi-project wafer services with affordable access to foundries worldwide, fabrication and travel assistance, value-added packaging and assembly services, and of course, in-house expertise for first-time right prototype. As for Lab, It consists of device validation to system demonstration, and this includes access to leading-edge platform to design microsystems and prototyping environments, access to test equipment and loan, and access to contract engineering services. And we offer technologies in different spaces, including microelectronics, photonics, microfluidics, MEMS, and embedded systems. And we offer this through engaging strategically in Canada and worldwide. We have partners in Canada and worldwide, and this includes access to MNT labs, CAD providers, labs, and access to fabrication services. This is a high-level overview of the CMC Cloud Unified Architecture. It consists of, this is a freshly newly deployed. It consists of a virtual infrastructure, accelerator, cluster, compute infrastructure, and storage. And it allows seamless transition between all these environments. So the cloud, the CMC Cloud design environment provides researchers basically with secure, high-performance, remotely accessible EDA resources for design of advanced microsystem and nanotechnologies. And here at the bottom left, I have the stack for this. So it consists of pre-configured transparent license configuration, persistent storage, process, PDK, and pre-installed, pre-configured CAD tools. So you have all this in one environment. So you don't deal with the different issue with setup and setup for the license and setup for other things. These tools such as ANSYS, Console, Xilinx, and other can benefit from tremendous speed up using a high-end CAD compute cluster, which consists of 8 nodes. So this is really for accelerating CAD tools. The second element is our topic today is the cloud FPGA GPU cluster, and now I'm going to show some of the features of this cluster. So we start with a small cluster which is in 8 nodes. It is powered by high-end server class CPUs and a lot of RAM, 192 gigabits of RAM. The connectivity between the nodes is 100 gigabits. This is very good for application that can scale from one node to multiple nodes, 10 gigabit to storage. And most importantly is at the right of this slide, this is the configuration of our starting point cluster. It's 8 nodes. So you have the configuration. We have 3 nodes that contains 2 GPU V100, 2 nodes that has 1 GPU, 1 FPGA, and 3 nodes with 2 FPGA. And as you can use, depending on your needs, one of these nodes to do your research. For example, the first 3 nodes, which has 2 GPU each, can be efficiently used to do training of machine learning application. So you can train in 1 GPU and scale up to 6 GPUs. As the second, it combines the GPU and FPGA and as a workload for heterogeneous computing, which an application can have a task that's run on GPU and another task that run on FPGA. So this is ideal to do heterogeneous computing research. Or you can do in the same node training on a GPU and inference on the FPGA. And the third one is 3 nodes with 2 FPGA, which can be used for a variety of workload that I will summarize in the next couple of slides. The software stack, so we run Docker container for the software stack, and this is fully validated working environments in the actual cluster. So if I start with the application, we support application from machine learning application with very well-known frameworks supported by vendors, Caffe, TensorFlow, MoxNet. These are the 3 frameworks that we support today. As for other workloads, is supported by the cluster or can be supported by the cluster are database, video, finance, genomic, and we can add other applications if researchers are interested to. We can help them set up the environment to support other workloads. The second layer is the middlewares, tools, and libraries, and these are very essential in order to run this. You need to download and install these libraries that are provided by the vendor to accelerate some applications. For example, CUDA neural network is a library from NVIDIA, and it is optimized for GPU architecture for training a deep neural net. And we have set up all the libraries required, so you don't have to worry about any required one. At the right of this layer, there are different models that are supported, including OpenCS, C++, and Python. The runtimes combines runtime from different vendors, so basically from Xilinx and from NVIDIA. And these runtimes allow you to offload processing from your application to the required hardware. And the last layer is the hardware accelerator, which is in our case a combination of the GPU and the FPGA. So as I said in the beginning of the presentation, the FPGA GPU cluster can be used for different purposes. And here we summarize some of the most important one. First one is the machine learning, training, and inference. I have a complete software stack that is validated for Caffe, TensorFlow, and MoxNet. And other workload that can benefit from this compute cluster include quantum chemistry, molecular dynamics, climate and weather genomic. Video processing transcoding in the FPGA is very popular. Financial computing as well, database analytics and networking. So depending on your research orientation and needs, you can use this cluster for different workload, different purposes. I'm going to highlight some of the important platform in that space that CMC is supporting. And this is an end-to-end deep learning platform. And I show here the 3 basic steps for machine learning. You don't need in the beginning a high-end cluster to do some prototyping. So basically you can have just TensorFlow or Caffe working on your desktop and just to design a network and make sure that your data is well prepared. And then when you need acceleration for training, you can switch to the FPGA GPU cluster, where you have access to basically GPU for training, because FPGA is not designed for training as we speak. There are some research that demonstrate that FPGA can be used for training, but I didn't see any framework for Xilinx that use FPGA for training. So we use the FPGA GPU cluster, the GPU part just for training. And once the training is completed, we can do inference. Inference, it consists of deploying the trained network in a real-time processing of data to do inference. Basically, inference can happen in the 2 spaces. In the cloud space at the top right of the slide is using the FPGA GPU cluster, and both vendors, NVIDIA and Xilinx, demonstrated good inference results for their platform. The second space is the embedded space. And here you have different requirements. It has to be high performance, very low power in order to be used in the field. And we support a platform called ZCU102, which is a Zinc platform. And a previous webinar already demonstrated how to deploy a trained network in this embedded platform. So to put all this together in one project, this is projects awarded to CMC by the IDEA, Innovation for Defense Excellence and Security. It consists of implementing a novel platform for AI-based object detection, classification, tracking using heterogeneous computing architecture. And here you can see all the ingredients needed to do that. So this is a 2 sub-project. The first one consists of training a convolutional neural network on a heterogeneous computing node. And then once the training is completed, we take the graph and we do the quantization, optimization to fit on the embedded FPGA that is shown here. So this is basically 5 steps. The data selection, network design. Here you select your network, your CNN network. You do the training on the GPU. We're going to see a demo today for that. And once the training is achieved, you deploy. In this case, we deploy for an embedded space, but we can also deploy on the FPGA and the cluster. As a background, there is already 2 webinars that are posted on CMC's YouTube channel. The first one is a deep dive to Caffe and how to use Caffe. We're going to have a very short overview of this today, just to make sure you appreciate the demo that we will show. And the second one is accelerating deep learning for embedded vision at the edge. And this is the second webinar that was developed by my colleague Hugh Smith. And it consists of showing all the steps required to do inference at the edge. And if you need to do that, you can take a look at this webinar. Now, some examples of Alveo of the FPGA workload acceleration. As I said previously, it depends on the application. Xilinx has partners that develop libraries and software for workloads from database search and analytics, finance, computing, machine learning, and depends on the application. They published some results on the Alveo card. For example, for database search and analytics, it's 90x compared to the CPU. In our case today, for inference is 20x. So these are some figures of merit using this FPGA. As for GPU, I want to show this example, which consists of training ResNet 50, and the speed up can reach 96x. So in people that are interested in accelerating machine learning, this is really a very important platform. And as we will see in the demo, we are going to show training on CPU and training on GPU, and you will see in real time the difference in speed. So this summarizes our infrastructure support for deep learning. Now we are going to have a short overview about the framework we are going to demonstrate today, which is Caffe. And Caffe, basically some features. So you need to understand this feature before using Caffe. The first thing is the data type that Caffe can ingest. And this is very important. So your database for training need to be built using LMDB database or HDF5. Training from raw images is also possible, but it's not efficient because you have a lot of latency accessing the files. So in our example, we are going to use LMDB. Once you use Caffe, you have some tools that are already available in build tools, and these tools allow you to do some processing. So it allows you to create the LMDB and generation of the mean image, which is a pre-processing step before the training. And shuffling, so you need to shuffle your data before training. All these scripts are already pre-compiled and ready to use in that directory. As for data transformation, there are other scripts that allow you to do image cropping, resizing, scaling, and mirroring mean subtraction. For example, resizing, you need to understand the resolution of your data, of your images, and you need to do resizing to adapt it to the network you are using. Some network, different network accept different resolution, so you need to understand that resizing is very important in order to make this work. The Protobus, so the Caffe use a model called Protobus. It is developed by Google, and it's a good method for serializing structured data. At my right here, I have an example of a network. So basically, each block is a processing block. For example, here we have convolution, here we have Gaussian filter. So each block describe what happened to the data in that come to the block. It is human readable and used to define the network architecture. So for people that start with Caffe, there is already more predefined models of CNN, including AlexNet, GoogleNet, VGG, SSD, and these different networks, you have already the files. All what you need is your data to train them. So we will show some examples in the demo. The pre-processing block, so there are many, combining loss functions, convolution polar normalization, and activation function. And here at the bottom of the slide, I have an example of a convolutional neural network. It takes images with the resolution. It takes an image, and the image go through different processing blocks. So there are two stages that are main stages for CNN: the feature extraction and classification. The feature extraction, any network use a series of convolution, polling, and activation layer. And classification use basically fully connected network and matrix multiply. In this case, we take an image, we do all the processing, and then we predict the class of the image. For example, here we have a boat by a probability of 0.94. And this is a case for inference. So for the example we're going to show, data preparation, we have here a database. It's a DLRSD dataset. It consists of 20,000 images, 21 classes. So we have 100 image per class. And these are from airplanes, beaches, buildings. So we have this, you can download it from internet and use it. It's publicly available. The script we provide, the first one consists of copying all the images from all these directories to one directory and create a two text file, train and val, which are required for the training. So we are going to see the contents of this file. And the second script consists of creating the LNDB with this resolution, which fits with our model. An additional step is creation of mean binary proto, which is used in the training as well. So to illustrate that, all the images, we execute this script, we put all the images in one directory, and we create val, txt, and train txt. Each of these files, they are the same, but each of these files is for a particular purpose. This is for validation, this is for training. It has two columns each file. The first one is the name of the file, of the image, and space and the class of the image. And this is to guide the training process. And the second step is the creation of the database, which is used for training. So we use directly these databases and not these files. The model definition, there is a variety of models available within Caffe. In this case, we use CaffeNet. So it's a replication of AlexNet. But we need to do some changes to the model provided by Caffe. And these are the changes we need to make on each model before training. We need to update the path to the mean binary, which is generated from the images we use. We need to provide the path for training, the database for training. And we need to change the number of output depending on number of classes we have. In our case, we have 21, but the original file has 1,000 because it was designed to train for ImageNet, which is 1,000 class. So here we have to do these changes. We can also visualize graphically the graph. So we have here a script that can display the graph so we can see the different layers, how they are connected, just to have a good understanding of what the CNN graph is doing. The solver, finally, before we go to the model training, the solver is a very important file. It's very easy to read. It just provides the path to your model that you need to train. This is what we described previously. And you need to do, set some parameters for the training. We are not going to cover that today, but for each case, you need to very carefully pick up the right parameter to guide the training. But some parameter like snapshots, each 2,000 iteration, we're gonna save the training results in a temporary file. And we provide the path where we're gonna save the results. Caffe model 1. Very important is the solver mode. Here we have GPU. It means we target the GPU architecture for the training, but it can be CPU if you want to compare the results in terms of speed. The model training, consists of a very simple command. So you just need to issue cafe train and set a path to the solver we just provided. And the solver set the solver here. The cafe can find the path to the model that needs to be trained. Here we save the results of the training in a log file, and we can also see in the terminal the progression of the training. So once the training is completed, we can plot the results graphically in a script that we provide. And here, since we trained this model from scratch, we have achieved the 85% of accuracy after 4,000 iterations. There is a technique called transfer learning that's improved these results. So instead of training a model from scratch, you can train a pre-trained model on your own data set, and here's the result. Before that, CNN is a type of deep neural network that benefits from a lot of data. So using a pre-trained network can help with the training results for your case. So instead of training a network from scratch, transfer learning trains an already trained model, and there is a lot of trained model online that you can use. In our case, we used something that is available through Cafe, which is a pre-trained model on ImageNet. So as you see, the difference here, we train our model, but we use a parameter called weight to indicate to Cafe that we want to use predefined, pre-trained weight, and we save the results. So we go from 85 to basically 98, which is very good. So it's best practice in machine learning space is to use a pre-trained model for your problem to achieve a very good validation accuracy in a very short time. So this summarizes Cafe as a framework. It's very easy to use it, and there is a lot of documentation online. And these steps will allow you to train any model on any data set. And we have a tutorial to do that. Now I think we can switch to the demo. And the demo consists of two things. Training on Tesla V100 GPU and inference on the Alveo FPGA. So the training on the Tesla V100 GPU is going to be a very fast demo. While the inference, there is a step called quantization, which will take at least 2 to 3 minutes. This is where we're going to pick the questions. But let's start with the training on the Tesla V100 GPU. So what we're going to do, we have containers that are available in the cluster that you can simply load and start. And when you start it, it will give you the environment that you can use easily to train any model. So we're going to do that. And we're going to run, once the container is launched, we are going to, from Workspace, get some data, create the databases, and compare training for GPU and CPU. So this seems like a good demo for the GPU, which is fast. I'm going to switch to another window. Can we see the windows? So I have here two windows. I'm going to just detach this so I can benefit from more space. So I am logged to one of the nodes of the FPGA GPU cluster. I'll just resize this window. Perfect. And at the bottom of the screen, I have the list of the tasks I want to do. So I have this demo for the training. So I'm going to go to scripts. We have all what we need here. So the first thing, I'm just going to launch the container for NVIDIA. So I have a script that launched the container. I'm just going to copy it. So once the container is loaded, we can see NVIDIA Cafe. Now we can launch any command, for example, device query. So we have a GPU V100 installed with all the versions you need to know, the runtime version, the CUDA version, and all the capability of this. And from the workspace, I'm going to get some data for my model. This is a model that is given by Cafe. So I'm just going to get some data for training. And this script consists of creating the database, the LMDB database that I have mentioned. So I'm going to run this again. Copy. So here we create the LMDB for validation and for training and validation. Now let's take a look at a particular file. This is the proto.txt, is the solver file that I have mentioned in the presentation. This is where you have all the information you need for your training. So basically, as you see here, we have all this information that guide the training process. Here we have a directory where we store the results. And the solver mode is GPU, CPU. So what about we start with training on the CPU, and just to see how fast it will be. So I will save this. So I set it to CPU. And let's start the training. So now you're gonna see how slow it will be on the CPU. So it loads the model, then it starts slowly, one step after step. And then it starts the training, which take roughly, I think, half hour or 26 minutes. I don't remember the time it will take, but as you see, it's extremely slow. And imagine for a very complex network, it will take weeks. So let's stop this and change the solver to GPU. So I see it's very simple to switch between GPU and CPU. So I'm going to switch it to GPU. I'm going to save and launch the same command, which is train the net. So I'm going to copy this again. Copy. Now we train on the Tesla V100. As you see, the speed is very fast to train on this accelerator. So for people interested in training crazy network on large data sets, this is the best place to start. So overall, I showed the basic step to train any model on any data set on the GPU Tesla V100. And of course, we are going to make the example I showed in the presentation is going to be available. It's going to be accompanied with a tutorial so people can follow the steps and replicate the same result. As for complex network, we are always happy to help if you need any help in implementing or getting anything implemented in the cluster. Now I'm going to exit this Docker container and get ready for the FPGA part. But before going to the FPGA part, I will go back to the presentation and just summarize what we're going to do. So the inference on the Alveo, I have just one slide here to show the flow that Xilinx made available in order to do inference on their Alveo FPGA. They support TensorFlow, MoxNet, Caffe. They have a container for that. And there is a very important step to understand here is that the FPGA require quantization. So the first thing is the front end. So basically, Caffe generates a network that will be translated by framework tensor graph to Xilinx tensor graph. The Xilinx tensor graph is a graph that Xilinx tools will understand. the result is a tensor graph optimized for the Alveo architecture. Then it goes through quantization, which use the model weights. So basically, it's a translation. It's a conversion from 32 bits to 8 bits in this case, and the calibration set. The compiler is very important to understand too. It generates all the steps required. So basically, you have a graph and you have a scheduler that the runtime will run, which layer will be running on the CPU and which layer will be running on the FPGA. And we are going to go through this flow in the demo. So I will go back to the demo. I will just, so I exit the container, and the demo for the FPGA is a little bit longer than the one for the GPU. So first of all, I'm going to go to the Xilinx directory. And by the way, when you access the cluster, you will have this same format, the same directory structure as this demo. So you will just follow the steps I provide here. So the first thing we're going to do is to load the container provided by Xilinx. So we're going to issue this command, copy. This will take at least 45 seconds. So we can take one question. How many questions we have in the chat?
I think there was one question, but it looks like it was answered already.
Okay. Please feel comfortable asking any question in the chat window. So when we wait for some comments to load, we will be answering questions. By the way, this command you need to issue it just one time in the beginning, and then you can launch and interact with the container using a script that is available in the same directory. So we are going to launch it here. So we are inside the container of Xilinx here. So you see the directory has changed to ML Suite. The demo consists of running Caffe Inception V2 SSD model. And the first thing we're going to do, of course, when you do changes on the container by downloading new data, changing script, loading your own script, you can save the state of your container. So when you come back and load it again, you have your data saved. Just in the case of this webinar, we show you how to do this from scratch. And also, I want to notice that there is a directory that is shared between the container and the host. And this directory will allow you to exchange data between the container environment and the host environment. And you can look at Docker run sh to know where it is mapped. Or I can answer a question about that after the demo. So the first thing we're gonna do, we're gonna download the data set for this example. And as a step, I'm going to position myself in the directory where it is the reference design SSD detect. I'm going to copy the data from the host to the container. So this is the directory I was talking about. It's called share. And this is where I put my data before launching the container so I can communicate with. So we're going to copy this data. Now it is copied. We're going to extract the data. So it's all extracted. And we're going to generate the ground truth file. And this is a file used by the SSD. Basically, it just take each image and draw boxes around the objects of interest. We are going now to get the necessary models. So we need the model that Caffe use. For this case, the SSD, and we're going to download it from Xilinx. So the script I created is get SSD, And there is another script gets all the models, but we are not going to download all the models today. We're just going to get the SSD that will be used. After getting this file, we're going to just run this command, which consists of downloading the model from Xilinx. So this is all what you need from Xilinx about the model that is compatible with the FPGA, all these things. So basically, when you have a model that is trained on the GPU and you want to use it for inference on the FPGA, you need to change some blocks manually in order to fit with the FPGA flow. In this case, Xilinx did the job. They already offer these models that are compatible. So for each well-known model, such as GoogleNet, AlexNet, all these models, you can find them at Xilinx. So you don't need to do any manual modification. Now, since we get that, we need to set up the environment for the FPGA. And this basically set up the board with the overlay. So for people that are not familiar with the overlay, here, the overlay, it's a hardware that is already mapped to the FPGA that is based on processing element that will run the graph. So you don't do any hardware design here. This is really for software developers that would like to accelerate inference on FPGA. So for Xilinx, they made available many overlays. We use one of them here for this example. What it will do is to load the overlay to the FPGA. It's pre-compiled. And when you quantize your model, it will run as instructions. So there will be a lot of communication between the host CPU, which run the application of the inference, and the FPGA, which accelerates some tasks of the inference. So this is well documented, but we'll demonstrate that now. So after issuing this, we set up the environment for Alveo U200. This is the environment we have. And then we are going to prepare for inference. So this is very important because here we will run the quantization tool. So I'm just going to see, I am already in this directory. So this command, run the quantization tool and set up for inference. So this will take some time, at least I think it's 2 minutes. And what about we take some questions?
Okay, there is a question about the Docker containers.
Yes.
Are they available for desktop prototyping? Where do they get them?
The Docker container that these vendors make available, they are built for their own card. So they really run for either GPUs or FPGAs. I am not sure if you can run them on your desktop, but if you can try. You can download the container, for example, from NVIDIA, and then set up the training for CPU, because if you do GPU, it won't be available there. So I'm not sure if there are containers that will work for sure for desktops. Because the way I set up the cluster, I already installed the drivers, the runtime for the GPU. So when I installed the container, it looked for these things. And if they don't exist, the container won't install. In your desktop environments, the GPU doesn't exist. So I'm not sure if it will run properly. Any other question? So we can see here the progress of the quantization. You need to do this for each network you would like to deploy, but you do it just once because after that it will be used for inference. So we do a lot of optimization. It do the resolution from 32-bit to 8-bit. It does all this, and now we are going to run the inference. So inference consists of providing an image to the network, and the network will work on it and tell us what it is. Okay, so I have here some images, test pictures, and we are going to provide, for example, the first one is a horse. So I mentioned here that it's 22. So 22 is a horse. And the second picture we're going to test is a cat. So it's 19. So I'm just going to take this command, issue it, and see. So it's going to load the network. It's going to offload the processing to the network. And here we have, for the first one, it's a horse. It tells you the exact location of the horse in the image. And let's try another one. So this is for the cat. So as you see, it's a cat. It tells you the forward time and also the location of this. If we run the other example, if we rerun this example, so SSD is a very interesting model. It detects multiple objects in the same image. So if I check here, it detects a horse and a person. And it gives you the exact location of these two, right? Because here we have a horse and a person. So here we demonstrate image by image the inference, but it gets more interesting when you process video feeds, but you need to implement all the video pipeline and all these things, which make your application more complex. And we will cover this in a future webinar. I think it's time to take some questions. And please contact me for any request. If you need to access the cluster, you can contact me and I will provide you with pleasure the access and work with you in order to get the most of it. And as we progress in time, we are going to make more complex reference design and example use cases for the cluster, not only for machine learning, but we are in the process of making other reference design that are not related to machine learning. For example, hardware software exploration on the Alveo card, which use completely another flow. But we would like to build a community around this and people accessing it and share with us the results, and maybe we can extend it to even more nodes in the future. So we'll take the questions now.
Okay, there is a question on how hard is it to perform an FPGA on-chip training instead of GPU?
I'm not expert in that space, but I came across multiple papers that try to do that, and it's not impossible. If you have my email at the end of this presentation, you can contact me and I will be happy to share with you these papers. I know that this question was asked to Xilinx in one of their webinars, and they justified that they don't support training on FPGA because most of their clients they are in the inference space. But there are hot research topic to do training on the FPGA. Yes.
Another question, are the scripts you're running created in-house or are they available through the vendors?
Both. So the examples we showed today, there are some scripts that are developed by the vendors, but the example I showed in the slides is completely developed at CMC for the IDEA project that I was talking about. So it's a combination, but in your case, you always need to, for a particular case, you need to create your own.
Question about the cluster. So how would one create their own solution on such a cluster? And are they able to do that, or is it more efficient to use transfer learning from already compiled vendor-ready solutions?
This is a good question. In most cases, transfer learning is the way to go to fine-tune your model to a particular problem. In the case of this software stack, we recommend to use vendors' models because they are already optimized. But in the case where you come up with a new model that you describe in Café using Protobus protocol, then you are on your own. You need to train it on ImageNet and then fine-tune it for different other tasks.
Oh, one other question in. Is there any available library with different IP, like transfer function with logic?
With logic?
Yeah.
This is a completely other flow. So I guess the question is to use hardware IPs that will be mapped to the FPGA. So Xilinx with their collaborator, as I showed in one of the slides, in different application domain, they have libraries that you can purchase, or we can also make available if it's needed on the cluster. But this is another flow that we will for sure organize a webinar to do that. This is SD-Accel flow, which allow you to use different programming models to do hardware-software exploration, but basically OpenCL. So how to combine OpenCL methodology with IPs from vendors or from users using their own RTL. So it is possible, and we will cover that. So not only you can also send me all the requests and questions after the webinar if you come up across any interesting questions or any feature you would like to enable in this cluster. We will be happy to consider it.
Is there a demo or information using an Intel FPGA acceleration card?
Not at this point, but we are open to support new technologies if there is a request from our community. Yes?
Question about access. Do we have access to see all the design characteristics and consumption resources?
Absolutely, we will make this available. There will be there is already a web page for the cluster, and we're going to post everything there. So since we just launching it today, this is basic use. This is launch webinar, but as we progress, we're going to make available more tutorial and reference design to do power estimation, performance estimation, and all these things. We didn't test PyTorch yet, but it is advertised as one of the framework supported with Caffe. So we will test that. So there's a question. I guess what I was asking was more on the topic to make our own models compatible with the Alveo. It is easy, doable to make a custom model compatible with the FPGA accelerator stack. I am talking more of a self-sustained prototype perspective. So if I understand well the question, when you say your own model, you mean your own design, and there is different entry point to the Xilinx flow on the Alveo. And there's already a lot of reference designs available from Xilinx to do that. This is using C or OpenCL or even RTL, or mixing all these together. So yes, there is an entry point for users bringing their own model to this accelerator. If you are talking about the machine learning stack, if you use Caffe or TensorFlow, you can design your own graph and try to train it. So this is a learning process. So you need to try different things, but it is possible to do that. So I think this was the last question. Do we have any other questions, Brent?
No, that was all posted.
Okay, well, thank you very much for your attendance today. I am looking forward to work with you and enhance your experience on the FPGA GPU cluster. Have a nice day.